One of the things that's always good for me to do is a couple of examples where I go through important molecules or ions and apply the 5 steps to draw Lewis structures and then some VSEPR interpretation so that we can see what we could learn about molecules by using these theories. So let's see, a classic would be NH3, so just ammonia. And if we look at ammonia, we have 5 valence electrons for the nitrogen, plus 1 for each of the 3 hydrogens, so we have 8 total electrons. So the first step for doing Lewis structures is, from the formula, we could determine how many total valence electrons, and so ammonia has 8. The next step is to connect the atoms with single bonds. So we get the 3 hydrogens attached to the nitrogen, and that uses 6 of our electrons, and so we have 2 more that we would normally fill the octets of the non-central atoms, but hydrogen only gets 2 electrons in its environment, so just attaching it to a central atom pretty much sets it up. And so at the end of filling octets of the non-central atom, we still have our 2 electrons left, and we put them on the central atom, and now all 8 electrons are accounted for, and nitrogen now has 2, 4, 6, 8 electrons in its environment. So very fine Lewis structure. For VSEPR, we want to look at the number of electron domains. So I count 1, 2, 3 atoms and 1 lone pair on the central atom. So I have 4 electron domains. And that tells us that the electron domain geometry is tetrahedral. So the electron domain geometry is tetrahedral. And if I wanted to draw this more in perspective, I would use the wedges and dashes to do the sort of tripod of atoms at the bottom, and then put the lone pair on the top. So here's more of a picture of a tetrahedron. And that shows us a little more about the shape of the molecule, because the lone pair of electrons, although it's there and repels the hydrogens and pushes them down towards the bottom of the molecule, this is invisible. So if you looked at the shape of the molecule, the lone pair of electrons would not be visible, so you sort of visualize the shape without the lone pair of electrons, and that would be called a trigonal pyramidal shape. So if you had the nitrogen and the 3 hydrogens, the 3 hydrogens would be forming the base of a 3-sided pyramid, and so the trigonal pyramidal structure is this one. The tetrahedral electron domain geometry is that one. And the difference is, if we imagine being able to see the lone pair, we could see the tetrahedron. If we realize it's invisible, but it occupies space and forces the hydrogens closer together, then we see the trigonal pyramidal. And bond angle wise, a perfect tetrahedron, the bond angles would be 109.5. The lone pair is a little more repulsive than the bonding pairs, so this lone pair is pushing the hydrogens a little closer together than they would be in a perfect tetrahedron. You actually see a 107-degree angle there. What most people will put as an answer for that is less than 109.5 degrees, because the lone pair is pushing the hydrogens a little more together, but we generally don't really know how much together unless we memorize some bond angles. So there's a little picture of Lewis structure of ammonia. It is a 2-dimensional representation, and then when we visualize what it looks like in 3 dimensions, that's when we pull out the VSEPR and look at the electron domain geometry and shape. Okay, so let's do a couple more examples. Let's do an ion. And so if we did nitrate, NO3 minus, nitrogen has 5 valence electrons. Oxygen has 6 for each oxygen, and there's 3 oxygens. And then to get the negative charge, we add in 1 more electron. So counting the valence electrons in nitrate, NO3 minus, we have 6 times 3 is 18, plus 1 is 19, plus 5 is 24 electrons. Alright, so then we connect the atoms with single bonds, fill the octets of the non-central atoms, which the last one, our non-central atoms, were all hydrogens, so we really didn't worry about that. But the oxygens do need a nice hearty lone octet of electrons, so we add in the lone pairs. And then this uses 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, all 24 electrons, so we don't have any more to put on the central atom. So at this stage, we're not allowed to add any more electrons because we've used all we have. And this is where the 5th step comes into play, because if this nitrogen only has 6 electrons in its environment, the 3 bonding pairs, it needs 2 more. So what it's going to ask is that its neighbor shares with it, boom, like that, and that's going to form the multiple bond. So the nitrogen is double bonded to one of the oxygens and single bonded to the other 2. Voila, like that. And now we have the right number of electrons, 24. Every atom has 8 electrons in its environment, so that's good. And the overall charge on this would be -1. And as I've mentioned before, this double bond and these 2 being single bonds makes it look like one of them is shorter than the other 2. So we have to invoke resonance. And rather than just showing the left oxygen as the one that could share, we also have to work in the possibilities where the bottom oxygen or the right oxygen could have shared. And so they sometimes are going to be the double bonded one. So there's another resonance form of the nitrate. And then we have the other one where the double bond can be to the right instead. So to show the equalization or averaging of the 3 bond lengths, we need the 3 resonance forms. One where the double bond is to the left, one where it's to the bottom, and one where it's to the right. And there's our resonance forms. The other thing we should worry about is the formal charge, right? The formal charge. So when we think about each oxygen would have 6 electrons that it owns, or would be assigned to it if it was a neutral oxygen. This oxygen here has 1, 2, 3, 4, 5, 6, 7 electrons I would assign to it. It has 6 all to itself, plus it gets 1 from the shared pair. So the bond, 1 electron to each atom for formal charge assignments, so the single bonded oxygen is -1. And you'll see quite a bit of that, because every time you have a single bonded oxygen obeying the octet rule, it'll have 6 lone electrons all to itself, plus it gets 1 from the shared pair, making 7. 7 is 1 more electrons than oxygen would have if it were neutral. The double bonded oxygen, 1, 2, 3, 4, all to itself, plus 2 from the shared pairs is 6. That would be a neutral double bonded oxygen. And then the nitrogen, 1, 2, 3, 4 electrons from the shared pairs. A neutral nitrogen would have 5 electrons, so 4 is 1 fewer, so this is formally positive. So there's formal charge determination for the atoms in this ion. And if you add up the formal charges, -1 plus -1 is -2, plus +1 is -1, the sum of the formal charges should equal the overall charge, right? The overall charge. So then that's a good dot structure. Once we put in the resonance and the formal charges, we don't have to list the zero formal charge. A lot of times, especially when I'm teaching, I'll do that for redundancy and super clarity, that I have thought about that formal charge and I know it's zero. But if we didn't label the zero formal charge, that's okay. I'm going to go ahead and label it anyway. Alright, so the other thing that just came to mind when I'm doing these that I didn't do in the last example is add in the hybridization. So as soon as somebody tells me there's 4 electron domains there, I know I'm accommodating 4 things on the central atom, a lone pair and 3 atoms. I know I'm going to need 4 orbitals involved, so that means I'm going to need the 4 sp3 hybrid orbitals. So in order to prepare for bonding, the central nitrogen is going to be sp3 hybridized. Now when I look at this structure, I see 1, 2, 3 atoms and no lone pairs on the central atom. So I have 3 electron domains, which means the electron domain geometry is trigonal planar. So it's okay that the dot structure shows this sort of as a T-shaped molecule, but in actuality the atoms get to spread out more in space and form a trigonal planar geometry. And if there are 3 electron domains, we need to have the 3 hybrid orbitals, and we use the 3 atomic orbitals to build them. So we have sp2, we use 2 p orbitals and an s orbital to get the 3 orbitals to form the 3 electron domains, and then, as we'll learn later when we talk about hybridization, the 3 regular atomic orbitals hybridize to form 3 sp2 hybrid orbitals, and they form the triangle we need to have the actual geometry of the molecule. So this triangle with the 120 degree bond angles is the right shape for nitrate, and although our dot structure is correct, it does not show the geometry explicitly. Alright, so the electron domain geometry is trigonal planar, and then the shape of the molecule is again what we see in terms of the atom arrangement, realizing that the lone pairs of electrons are invisible. And in this structure, we don't have any lone pairs of electrons on the central atom. None of our electron domains are lone pairs, which means the shape is going to be identical to the electron domain geometry. So if there's no lone pairs of electrons on the central atom, then the electron domain geometry is formed strictly from atoms. So the arrangement of atoms is the electron domain geometry. The shape is the electron domain geometry. So there's a couple of examples of straightforward dot structures and applying VSEPR to get the electron domain geometry and shape of the molecule along with the hybridization. So I hope this is somewhat helpful.